All right. I know right now what you're thinking is, please, Bob, give us more examples. Of course I will. So here we go. Here's another example where we're going to do everything. We're going to look at the domain, figure out the important limits, and construct the sign table, and then construct a possible graph out of these. So here we have a piecewise defined function f of x. F of x is equal to the formula 1 over 1 minus x if the input is strictly less than 1. If the input is 1, so the output. So if the input is 1, then the output is 1. And if the input is strictly bigger than 1, then the output is computed as x minus 1 over ln of x. All right. So when you have a piecewise defined function, it's a bit annoying because you have to compute the domain of the equations and then check if it works over the restrictions. So for example, this equation here, the first equation, if you're computing its domain, so we only have a division by 0 when x is equal to 1. So this is defined everywhere but at 1. So from minus infinity to 1, union 1 to infinity. So this would be the domain of the equation, but because this function is only using that equation before 1, and here before 1, we are over its domain correctly, we have no problem with this equation. So the function here is not going to crash. F is not going to crash before 1, strictly before 1. Of course, at 1, it's not going to crash. We know how to compute the output. It's simply 1. What about before, after 1? So if we look at the equation after 1, if you compute the domain of x minus 1 over ln of x, ln of x, of course, is crashing if the inside is strictly negative, and it's also crashing if ln of x is equal to 0, and this will happen when x is equal to 1. So actually, the domain of that equation is from 0 to 1, union 1 to infinity. So before 0 and or at 0, it crashes because of the logarithmic term. At 1, the logarithmic term does not crash, but you get a division by 0. But that's all right. Even if this domain is kind of complicated for the equation, because f of x is only using it after 1, then we have no problem. So the function f actually, it's kind of weird, even with all those restrictions, it never crashes. It does not matter what the input is. The domain of f of x is actually everything. So here from minus infinity to infinity. So this function f of x does not crash because 1 over 1 minus x is all good, strictly before 1. At 1, it's good, we get 1. And x minus 1 over ln of x is also all good for x strictly bigger than 1. So automatically from the domain, okay, we have two important limits. So we have at minus infinity and we have to plus infinity. But we need to remember that there is a change of equation. So even if f of x is never crashing, we're changing equation around 1. So this means that because f of x is changing equation around 1, that we need to study what's going to happen with f before and after 1. So here, so when you're going to define important limits, so as a remark here, because we change equation at 1, this function, f of x, we need to study its behavior before and after 1. So now we get another two important limits. Approaching 1 from the left, I'm going to call that 1, 3, and to the right, I'm going to call that 1, 4. So 4 important limits, so 4 tables for us to construct. So 1 is when x goes to minus infinity. Again, here the order does not matter. The second one is when x goes to plus infinity. And then the third one is when x goes to 1 from the left. And the final one is when x approaches 1 from the right. So remember, one of the first things that you have to do is construct these tables. So make sure you understand like which inputs are going to be used in order to compute outputs to guess these limits. So going to minus infinity, of course, I'm going to use my classic minus 10, minus 100, minus 1,000. Going to infinity, I'm going to use 10, 100, 1,000. Going to 1 from the left, I'm going to use 0.9, 0.99, and 0.999. So 3 numbers very close to 1, getting closer to 1, and smaller than 1, and then bigger than 1. So for the right limit of 1, I'm going to use 1.1, 1.01, and 1.01. So I'm expecting in any evaluation, when you're constructing a table to guess a limit, that you have at least three inputs. Okay, so now let's fill up these tables. Okay, so for the first table, so at at minus 10, minus 100, and minus 1,000, if you compute outputs. So remember here, I'm just using the function. So for negative infinity, so for these numbers, they're all less than 1, so you are using 1 over 1 minus x, by the way. And then when you're computing output, boom, okay, these are the outputs you're going to get, 0.909, 0.0099, 0.000999. So these numbers are all getting closer and closer to 0. So my first guess here, so for my first limit, this is a guess for limit going to minus infinity, you're going to get 0. And of course, since we're here, what does it mean that it goes to 0? So this means that we have a horizontal, so this is a visual conclusion, we have a horizontal asymptote. So HA, so conclusion, sorry, my pen here. So conclusion, we have a horizontal asymptote, and the equation of that asymptote is y equal to 0. So now let's go to infinity. So again here, because I'm going to use 10, 100, and 1,000, I'm going to be using the equation x minus 1 over ln of x to compute the following outputs. So here we go. So here, boom, okay, those are my outputs. At 10, I get 3.9, at 121 point some shit, and then at 1,000, 104. So you get numbers that are getting bigger and bigger. They're not getting closer to anything. So here, if I have to guess, okay, my guess going to infinity. So this is my limit going to infinity. It's going to be infinity. So on the rightmost side of the graph, no horizontal asymptote. Okay, this function will go up forever. Now on the left side of 1, so on the left side of 1, again here on the left side of 1, I'm going to use the first equation to compute the following outputs. Boom! Okay, so 10, 100, and 1,000. Again here, these numbers are getting bigger and bigger. So my guess here for my limit going to 1 minus is going to be, so 1 minus, so x goes to 1 minus is going to be 1 minus is going to be infinity. And as soon as you compute a limit around a number and getting infinity, you can have the following conclusion. So we have a vertical asymptote at x equal 1 because we're blowing up to infinity around a number. And now if we're computing outputs on the right side of 1, I'm going to use the other equation. So make sure you know how to compute outputs here. This is crucial. If you can't compute the outputs, you cannot guess what's going on here. Boom! So you get 1.049, 1.0049, 1.0049. So here my guess here is that on the right side of 1, I'm going to get 1. So here potentially, so this will be kind of a tougher one, but potentially here we have a hole at 1, 1. Why 1, 1 here? The x coordinate is given by the x value, by where we're computing the value, and then the y coordinate is actually the value of the limit that we are guessing right now. All right, next, let's do the sine table. All right, for the sine table. So first we know that the function does not crashes anywhere, so we won't have like a column for where the function is undefined. What about the roots? So if we look at the equations here, so let's just write this as a bunch of remarks. Boom. Okay, so 1 over 1 minus x. So the first equation here before 1, this one has no roots because the numerator is 1 and it's never going to be equal to 0. What about the second equation, x minus 1 over ln of x? The numerator could be 0 if x was equal to 1, but remember we're using this equation for x strictly bigger than 1, so for any values of x after 1, the numerator is never going to be 0. So we have no roots whatsoever, but if you are constructing a sign table of a function that changes equation, so here we know there's a change of equation, so I'm going to construct a column for that point x equal 1 where it changes equation. So here 1 is going to be a special column, and I know that at 1 my function is equal to 1, so poof. So 1 is going to be a special column. I know it's going to be positive because f of 1 is equal to 1 by definition. And then I just need to worry about what's up before and what's up after. So here for before, so before 1, we're talking about minus infinity to 1. And after 1, we're talking about 1 to infinity. And now if you fill up the signs, so if you fill up the signs here, so if I pick a value before 1, let's say we pick 0. And after 1, let's say we pick 2. If you compute the output at 0 and at 2, boom, okay, you're going to see that it's positive everywhere. Okay, so here's my sign table, and basically this function is always positive. It's always above the x-axis. It never crosses it, and it's never below it. So now let's go and try to put all this information together, domain, important limits, and the sign table to draw a possible graph for our function. All right, now for the graph. Again here, one thing that I like to do for the graph here is to draw first any horizontal or vertical asymptotes. And if you have any holes, might as well draw them. Okay, so first, let's just draw the asymptotes. So we know here that there's an horizontal asymptote at y equals 0. And there's also a vertical asymptote at x equal 1. So I'm going to draw those first. Okay, boom. Okay, here are the asymptotes. Oops, sorry. Boom. Okay, these are the asymptotes. So at x equal 1 and at y equal 0. So I have my horizontal asymptote in orange here and a vertical asymptote here in red. I like to write the equations under, and when you're drawing a graph, I'm expecting the equations to be next to it. We also have a hole. The hole is at 1, 1. So if you draw the hole, might as well. So here we go. So I'm going to draw the hole here at 1, 1. So I have a hole at 1, 1. So a hole dot. But there's something special here going on. We know that the equation, so if you compute the output at 1, it's equal to 1. So this hole that we computed because of the limit, actually it gets filled up. Because my output is 1 at 1, so we know that f at 1 is equal to 1. So now I need to draw a full dot at 1, 1, then what happens is that it fills up this dot completely. So this hole initially, because it's a limit, because limits, they compute holes initially, gets filled up. So there's no hole in the end, there's no hollow dot because it gets filled up by f of 1 equal to 1. So if we add like the exact same equation for f of x, but suppose that we did not add that middle line, this would just stay a hole, or if my function was f of x is equal to 2 at 1, then the full dot would have been above that full dot. Okay, so anyways, now I am ready to draw my graph. So before minus infinity, okay, so before minus infinity, around minus infinity, not before minus infinity. You cannot be before minus infinity unless you're the daughter of God. Okay, so here I need to draw something that is positive and that is very close to y equal to 0. So boom, okay, that's perfect. So here what I'm going to do is I'm drawing something that is always positive. And then, so here what's happening, so if you think about the first important limit that we've computed together, you can see this graph here is very close to 0. And I know as I'm approaching to 1, I need to blow up to plus infinity. So that was the third limit that we've computed together. And then of course here, what you can notice is that the graph of this function is always above the x-axis, so it's positive. And now at 1, the function starts at 1, and then it needs to stay positive, and it needs to go up forever. So here we go, boom. Okay, so that's an example, that's a good example of a graph, of a branch, sorry, that is going up forever, okay, going to infinity. So if you are labeling the important limits here, you can see that this branch going to infinity here, that was our second important limit. And of course, also on the right side of 1, we can see that this graph is getting closer to 1 also. So again here, like when you're drawing a graph, always think about the 3 important parts. So first, this graph, if I'm asking you just visually now, okay, so this is the graph of the function. So visually, so my graph f of x, for f of x here, so is defined everywhere. There is an output for every single input, okay? And so it is consistent with the domain of my function. So there's no point x, okay, such that the function is not defined. What about the important limits? Well, we see them. So we see that on this graph going to minus infinity, this graph is getting closer and closer to 0. We see the horizontal asymptote. We see my second limit that we guessed together going to infinity. I see it. On the left side of 1, this graph goes up forever in the sky, getting the plus infinity. And on the right side of 1, I'm getting closer to that full dot. Initially a whole dot, but it gets filled up with the output here. So all my limits are good. And then for the important sign table, so we see it's positive before 1. It's also positive at 1 because it's equal to 1. And then it's positive again. So this function is always above the x-axis. So this is a beautiful graph, consistent with the domain of this function, the 4 important limits, and the sign table of that function. And since we're there, and because we love it, okay, if I'm asking you where is this function continuous, so if you're computing the continuous domain of that function, where do I need to lift my pen? Well, my vertical asymptote is forcing me to lift my pen at 1, so this function is actually continuous everywhere but at 1. So this is like a very nice example of a function where the domain, even if the domain is everything, the continuous domain, or the continuous, where it's continuous, is not exactly the same as the domain. And one of the reasons why this is happening, it's because I'm using 2 different equations. So we have a change of equation, and we see that these 2 branches sadly are not connected. It's not always the case. It's possible that you have 2 different equations that connects. So it could be continuous everywhere, but not in this case. All right, for that section, that's it. That's all. So bye-bye now.